recall that the sample mean is normal and its mean is the true mean and its standard deviation is the population's standard deviation divided by the square root of n. We assume that the null hypothesis is true, so that mu equals 1000. We're given that sigma equals 100 and that n is 50. So the sample mean will follow this distribution. In real life, you're usually not going to know the population standard deviation, but not the population mean. But we'll find out how to deal with that when we get to the t-test. Anyway, this is the reference distribution we use. If the null hypothesis is true, then the sample mean follows this distribution. The sample mean is 1025. The probability of drawing something at least as extreme as 1025 from this distribution is 0.077. And you can see how I'm calculating this. The probability of being greater than or equal to 1025 is 0.0385. Because I'm doing a two-sided test, I have to count the area that's just as extreme on the other side of the distribution as well. The p-value is this area, 0.077. The normal distribution is symmetric, so I can just double this area, but only do this with a symmetric distribution. The binomial distribution is usually not symmetric. Because 0.077 is greater than the significance level, we fail to reject the null hypothesis. We cannot conclude that the population mean energy consumption is different from 1000 kilowatt hours. To sum up, we specify a null and alternative hypothesis, we collect data, and compute a test statistic. Under the null, the test statistic follows a reference distribution. We calculate the p-value according to the reference distribution. If the p-value is lower than the significance level, we reject the null hypothesis in favor of the alternative. If the p-value is not lower than the significance level, we fail to reject the null hypothesis. You choose the significance level. The significance level is the probability that you'll make an error and reject the null hypothesis when it's true. So you might think that you'd always want to set it as low as possible, but there's actually a trade-off between type 1 and type 2 errors. You make a type 2 error when you fail to reject a null hypothesis that's false. If you set the significance level too low, your test may be too conservative and you might miss important discoveries. So you need to balance these error rates. The only way I know of to reduce both error rates at once is to increase n, take a bigger sample.